All right, question 1. This is from section 2.1. What I recommend doing for a problem like this is first finding out what that piece is, f of x plus h. So what we're going to do is take this function here, replace x with x plus h. So it's going to be 3 times x plus h squared minus 1. Now we're going to expand that. X plus h multiplied with another x plus h is x squared plus 2xh plus h squared. And then if you distribute the 3, okay, so now that we have this expression for f of x plus h, I'm going to create the difference quotient. Okay, this is going to go on the top left of that quotient. So we have so there's f of x plus h. Now we got to subtract f of x. And then divide by h. So we're going to have some like terms here that are going to cancel, 3x squared and negative 3x squared. This turns into a plus 1, which is going to cancel with that minus 1. So the only terms left are 6xh plus 3h squared divided by h. And then this h here is going to cancel with this h and one of those. So what you're going to have left over is 6x plus 3h. Question 2, this is from section 2.8. For part A and for part B, the steps that you take to find the inverse of a function is to switch the place of x and y and then solve for y. So for part A, if we're going to switch the place of x and y, and remember f of x is y, you're going to write x equals 2 times the square root of y minus 1 plus 3. Now we're going to subtract 3 here and subtract 3 here. So then that becomes x minus 3, 2 times the square root of y minus 1. Now we need to divide by 2 on both sides. Divide by 2, divide by 2. Now before we can add 1, we need to get rid of the square root. So we need to square here and then put parentheses and square that. And finally, add 1 and add 1 outside of the parenthesis. And remember to write this as the inverse of f. Now for part B, we're going to switch the place of x and y. And we have talked a lot in class about we don't want to solve equations involving fractions. So if we multiply both sides by the denominator, so if we multiply by y plus 3, multiply that side by y plus 3, what we would have, y plus 3 multiplied by x equals 2. Now we want to get y by itself, so I'm going to divide by x. And then finally, we want to subtract the 3 over to here. And this is equal to the inverse. All right, question 3. This is from section 3.1. So writing this in vertex form, first thing I would do is subtract 1. And then also factor out a 2. And then where the 1 used to be, there's a blank spot now. This is where we complete the square. If you remember, the formula we use there is half of b squared. So half of b is, if b is -6, half of that is -3. -3 squared is +9. So we're going to add a +9. And in order to keep the equation balanced, whatever we do on the right side, we have to do on the left side. But remember, it's not just a 9. 9 is being multiplied by 2. 2 times 9 is 18. So there's an 18 that's being added right there. So that becomes f of x plus 17 equals 2. Now x squared minus 6x plus 9 factors into x minus 3 multiplied by x minus 3, or x minus 3 squared. And then if we subtract the 17 back over, we're going to have f of x equals 2 times x minus 3 squared minus 17. So now that it's in vertex form, we can state the vertex. Let's move to the right 3 units and down 17 units. So the vertex is 3, comma, -17. Now, the graph provided here obviously is not going to fit that. Recommendation being just do the best you can. So 3, label the point, it's off the graph, and then excuse me, you still need to find the location of 2 other points. So if the vertex happens when x is equal to 3, I would choose x values close to that, like x equals 2. If you plug in a 2, 2 minus 3 is -1, squared is 1. 1 times 2 is 2. 2 minus 17 is -15. So 2, comma, -15, and then you could do symmetry. If the point you're graphing is off of the given graph, then you need to label the location of those points, just so that I know that no one's just making up points here, so label those points. This one would be 4, comma, -15. Okay, question number 4. For part A, given p of x, this is the general form, this is the factored form. So given p of x, list all of the possible rational zeros. We're going to use the general form for that. Remember, that's the p divided by q. So for part A, the factors for p come from -4, so that's plus or minus 1, 2, and 4. So then q, the factors of q come from the coefficient here, which is just plus or minus 1. So then p divided by q would be all the factors of p divided by plus or minus 1, which is just plus or minus 1, plus or minus 2, and plus or minus 4. So that's the answer for part A. Part B, typically we would only be given the general form polynomial, and we'd have to use the possible rational zeros theorem to find actual zeros using synthetic division. Luckily, we've been given the polynomial also in factored form to begin with. So listing the zeros is just a matter of looking at each factor. From this factor, one of the zeros is, so zeros we have x equals 1. From this factor, we have x equals negative 1. And then from this factor, x minus 2, it's being raised to the second power, which means there's 2 of these, x minus 2 multiplied by another x minus 2. So the 0 is x equals positive 2. That one has a multiplicity of 2. And that's important when we get to part C. Anything that has an even multiplicity, when you graph that 0 or x-intercept, it bounces. These two zeros have a multiplicity of just 1, which is an odd number, so for those x-intercepts, the graph crosses through. So for part C, sketching the graph, we need to show all the intercepts and end behavior. End behavior, remember, is determined by the degree of the polynomial. So for part C, we need the y-intercept. I'm going to start with that. If we let x equal 0, then we have 0 minus 0 plus 0 plus 0 minus 4. So the y-intercept is 0, negative 4. We technically already have the x-intercepts. We listed those in part B, but I'm going to list them now. One of them is 1, 0. Another one is negative 1, 0. And then the third one is 2, 0. And I'm just going to list here that this one bounces because it has a multiplicity that's even. And then for end behavior, the way I described it back in Unit 2 when we did section 3.4 and 3.2 graphing polynomials is just showing the end behavior quickly here on the little graph. Because it's a 4th degree polynomial and the leading coefficient right here, the leading coefficient is 1. That means both ends, the left end and the right end, are going in the same direction, and because we have a positive leading coefficient, they're both going upward to positive infinity. So end behavior looks like that. So we have the y-intercept of negative 4, x-intercept there, x-intercept here, and then an x-intercept at positive 2. The left side goes up to infinity, the right side goes up to infinity. So now we just need to connect the left side down to the right, over to the right side. So starting over here, at x equals negative 1, the multiplicity is just 1. There's one of these, so the multiplicity is odd. That means it crosses through. So it's going to cross through. It's going to come down to the y-intercept, and then it has to head back up towards this x-intercept. Now at x equals 1, this also is a multiplicity that's 1. There's only one of these x equals 1 x-intercepts, so it has a multiplicity that's 1. 1's an odd number, so it also crosses through. Then it has to come back down to that x-intercept. Now x equals 2, remember, had a multiplicity that's even, so it bounces when there's an even multiplicity. So it bounces off x equals 2 and connects up with that side there. So question 4, listing all the possible rational zeros and the zeros of the polynomial. That's from section 3.4. And then sketching a graph of the polynomial, we did a lot of that in multiple sections, but we started that in section 3.2. Question 5, this is from section 3.5. So we have given zeros, we need to create a polynomial that's degree 3. So if it's degree 3, it needs to start with 3 factors. So right off the bat we notice there are only 2 zeros given, which is only going to give us 2 factors. So the zeros are x equals 1, x equals 2 minus I, And what you need to remember, a zero that has an imaginary number or is a complex number like this always has to come in a pair. So 2 minus I will always come in a pair with another zero, x equals 2 plus I. So there are 3 zeros. We're going to use this bit of information at the end of the problem. This is called an initial condition. So first we're going to build a polynomial that's degree 3 with these 3 zeros right here, and then we're going to worry about this at the very end. So after you have all 3 zeros, and we know again we need 3 zeros because it's going to be degree 3, next step would be to begin your polynomial p of x in factored form. Each factor comes from one of the zeros. So if x equals 1, then x minus 1 is a factor. X equals 2 minus I means the factor is x minus 2 plus I. And then for x equals 2 plus I, we have x minus 2 minus I. Once you have it in factored form, you need to multiply these factors together. Definitely I would start by multiplying these two factors together first. The two factors that contain the imaginary numbers, multiply those together first. So it's going to be x times x times negative 2, x times negative I, negative 2 times x, negative 2 times negative 2, negative 2 times negative I, and finally I times x, I times negative 2, and I times negative I. So let's write those terms. X times x is x squared, x times negative 2 is negative 2x, x times negative I is negative ix. Now we're going to start with the negative 2 and multiply it to all three of these terms. So negative 2 times x is negative 2x. Negative 2 times negative 2 is positive 4. And negative 2 times negative I is positive 2i. And then finally the I is going to multiply to all three of those terms. So I times x is positive ix. I times negative 2 is negative 2i. And then I times negative I is negative I squared. Now you would go through and look for terms that can combine negative 2x and negative 2x combine to negative 4x. Negative ix and positive ix cancel. 2i and negative 2i cancel. And then remember minus I squared. So if I squared is negative 1, then that's really subtract negative 1. So that changes into a plus 1. So that plus 1 combines with the plus 4. So we have x squared minus 4x plus 5. And we need to multiply that x minus 1 now. So now we have px down to 2 factors. Now we need to multiply these 2 factors together. So that's going to be x times x squared is x cubed. X times negative 4x is negative 4x squared. X times 5 is 5x. Now the negative 1 multiplies. Negative 1 times x squared is negative x squared. Negative 1 times negative 4x is positive 4x. And negative 1 times positive 5 is negative 5. Combining like terms gives us a polynomial of x to the third minus 5x squared plus 9x minus 5. Now we're going to use the initial condition that p of 0 equals negative 15. The discussion we had in class recently, if you weren't there, hopefully you watched the video, was that this actually is only one of an infinite number of polynomials that satisfies this condition here, that is degree 3, and then it has the correct 3 zeros right here. What I mean by that is I could put a parenthesis around this polynomial and multiply it by any real number right there. And what that would do is still be a third degree polynomial. It would still have these 3 zeros, but it may not necessarily not satisfy this initial condition. Because what this is saying is you need a polynomial that when you plug x in for 0, you get negative 15 out for y, or for p. Right now, as it is, if you plug in a 0 for all the x values, you're going to get negative 5. What this is saying is when you plug in 0, you need to get negative 15. Now, a lot of students at this point could probably mentally come up with the correct answer for A. Excuse me, but here's the mathematics that should be shown. Negative 15 is going to replace p of x. 0 is going to replace x. And we're going to leave a as a variable. So negative 15 replaces p of x. And then if all of the x variables are replaced with 0, it becomes 0 minus 5, which is negative 5. So it's a times negative 5. If you divide both sides by negative 5, you get a equals 3. So what that means is you distribute a 3 to every single term to get 3x cubed minus 15x squared plus 27x minus 15. Question number 6 is from section 4.4. So write the expression as the sum or difference of logarithms. Another way of thinking about this is expand into several logarithms. And without exponents just means the very end you use the power rule of exponents. So what we have right now is a single logarithm. We need to use use the rules of logarithms to expand this into several logarithms. So initially, what we notice is we're taking the log of a quotient because it has a numerator and a denominator, so this is a quotient. So the first rule that applies is the quotient rule. What that means is you separate this into two logarithms. So the first one's going to be the numerator, and then we subtract a separate logarithm with the denominator. So that's the quotient rule. If we have the logarithm of a quotient, we can separate that into two logarithms using subtraction. Now we can apply the product rule because this first logarithm is x minus 1 to the 1/2 multiplied by y squared, so this is a product. So this logarithm expression can be separated into two more logarithms using addition. So it's log x minus 1 to the 1/2 plus log y squared. And we can do the same thing to this logarithmic expression because it's x plus 2 squared multiplied by x plus 3 to the 5th. So there's another product right here. So we can expand this logarithmic expression into two more logarithms. We have to keep this minus sign here. Now, here is a spot where a lot of students make a very common error. Right now, you're subtracting this entire expression. So if you're going to subtract the expansion of this expression, you need to subtract the entire expansion using a parenthesis. So it's going to be log x plus 2 squared plus log x plus 3 to the 5th, close parenthesis. Again, just reiterating, right now you're subtracting this entire single logarithm. When you expand it, you have to subtract both logarithms, so you need to put this in a parenthesis to ensure that you're subtracting the entire thing. Okay? Now the last step here is just to, like it says, without exponents. That's just the power rule, so each of these exponents is going to move in front of the logarithm, and I'm going to distribute this minus sign to both of these logarithms. So the final answer here is 1/2 log x minus 1 plus 2 log y minus 2 log x plus 2. And again, I'm distributing this minus sign here. So that's going to be minus 5 log x plus 3. Okay, question 7 Graphing logarithm functions is from section 4.3. So it's saying what are really the differences between log base 2 of x plus 2 and log base 2 of x. Difference here being obviously there's a plus 2, but what kind of transformation is that? Remember, this is inside the function. So it's a horizontal transformation to the left 2 units. Okay? We'll get to that later on when we start graphing this. Part A, part B, find the y-intercept, find the x-intercept. So for part A, to find the y-intercept, remember we let x equal 0. So if you let x equal 0, then we have log base 2 of 0 plus 2, which is 2. That equals 1. So the y-intercept is the point 0, 1. Find the x-intercept. That's where we let y equal 0. In this case, y is just g of x, so that one's going to be 0 equals log base 2 of x plus 2. So in section 4.5, we talked about how to solve this equation. This is just a logarithmic equation. You solve a logarithm equation by canceling the logarithm. Do you do that using a base? So I'm going to use a base of 2. 2 to the 0 power is 1. So this 2 to the 0 becomes 1. 2 to the log base 2, those cancel each other out, so you're just left with x plus 2. Subtract 2 on both sides, and x equals negative 1. So it's negative 1, 0. For part C, all logarithm functions, all graphs of logarithm functions have a vertical asymptote. Typically, it's right here at 0, unless there's horizontal transformations, and there is here. It's to the left 2 units. So the vertical asymptote, rather, is x equals negative 2. So we have a vertical asymptote at x equals negative 2. So there's the answer for part A, there's the answer for part B, here's the answer for part C. State the domain. So for D, the domain is on the right side. So the x values are from negative 2 to positive infinity, but we can't include negative 2 because negative 2 has a vertical asymptote. So it's going to begin at negative 2, but we're not going to include it. We're going to use a parenthesis, so negative 2 to positive infinity. Now for part E, they need at least 2 points on the graph, and we're pretty much done with that. We have the x-intercept and the y-intercept, so we just need to finish sketching the graph. Like that. Question 8 is from section 4.5. This is an exponential equation. The exponential term is the term that has the base and the exponent. So the exponential term is 3 to the x minus 1. This is what we need to isolate before we use a logarithm, because remember, the way to solve an exponential equation is with a logarithm. So that means we have to get rid of the plus 1 and the 2. So we're going to subtract 1 from both sides. And then we get rid of the 2 by dividing. So we have 3 to the power x minus 1 is equal to 4. Now the way to cancel a base is to use a logarithm. So the logarithm cancels the base. So we have x minus 1 is the expression that's left on the left side. On the right side, we have log base 3 of 4. And now finally, to get x by itself, we add 1 to both sides. And it doesn't specify what form of the answer, it just says solve. So right now we have the exact form. And if it's not specified, you're fine to leave it like that. Question 9 is from section 5.3, partial fraction. Now, part A and part B have different directions. Part A, find the partial fraction decomposition, is different, obviously, than when it says find the form of the partial fraction. So I'm actually going to do part B first because it's easier. The form of the partial fraction depends on how many partial fractions, and that depends on how many factors there are. So the denominator needs to be in factor form. This one already is. We have one factor here, x minus 1 squared counts as 2. So there are a total of 3 factors, so we're going to have 3 partial fractions. X minus 1 is a repeated factor. X is unique, it's by itself. So when we have a repeated factor, what we learned in section 5.3 is that you have to write this repeated factor as many times as it repeats. So if it repeats twice, we have to write it twice. And each time you write it, you have to increase the exponent by 1. So the first time we wrote it, x minus 1 here, that just had an exponent of 1. So then the next time we write it, we have to increase the exponent to an exponent of 2, which matches the one we started with. And then in the numerator, we're going to have a, b, and c. If it just says find the form of the partial fraction, then that is the form of the partial fractions. Part A is going through the whole process of not just finding the form of the partial fraction, but actually solving for the values of a, b, and possibly c to find the actual value of the partial fractions. The first thing we need to do is factor the denominator. So that's going to be x minus 5 and x plus 3. Because there are only 2 factors, that's going to give us 2 partial fractions. Now the next step is to multiply both sides by the lowest common denominator. The lowest common denominator is x minus 5 times x plus 3. I'm going to multiply this side by that, and then also multiply this side by x minus 5, x plus 3. So what's going to happen here is that's going to cancel with that. The numerator, or the lowest common denominator there, is going to cancel with x minus 5, x plus 3, leaving the numerator 3x plus 1. When we multiply the lowest common denominator to each partial fraction, when it multiplies to a, the x minus 5 cancels with x minus 5, so x plus 3 distributes to a. So it's a times x plus 3. When the lowest common denominator multiplies to the b partial fraction, x plus 3 cancels with x plus 3, so it's x minus 5 that distributes to b. So now we need to solve this equation for a and b. We have 2 unknown values that we're solving for. X is technically unknown, but we're not solving for it, so it doesn't really matter. The problem is with one equation, we can't solve for 2 variables simultaneously. So what we learned in section 5.3 is to choose values for x carefully that will cancel part of the equation, leaving us the one unknown variable that we want to solve for. So if I want to solve for b, then somehow I need to get rid of a, and we can do that by letting x equal negative 3. Because negative 3 plus 3 is 0, 0 times a is 0. So I'm going to let x equal negative 3. Every x variable becomes negative 3. Here it becomes negative 3. Negative 3 times 3 is 9. Negative 9. Negative 9 plus 1 is negative 8. Here, negative 3 plus 3 is 0, so this piece of the equation disappears. Negative 3 minus 5 is negative 8. Negative 8 times b is negative 8b. Divide both sides by negative 8, and you get b equals 1. Now, if I want to solve for a, then I need b to disappear, and that can happen if x is positive 5. So now I'm going to let x equal positive 5. So here we have 5 times 3, which is 15, plus 1. That's 16. Here 5 plus 3 is 8. 8 times a is 8a. Here 5 subtract 5 is 0. 0 times b means that part of the equation disappears. Divide both sides now here by 8, and we get a equals 2. So then the partial fractions are 2 over x minus 5 plus 1 over x plus 3. Question 10 is from section 5.5, and there's a component of it that's from section 5.4. So the first task is to graph the solution set. So the solution set would be the part of the graph that contains both of the shaded regions for each of these graphs. So I'll start with the first one, x squared plus y squared. If you notice and remember that both variables are squared, that's a circle. The radius is the square root of this value, so in this case the radius is 5. And the circle, the boundary, the outer part of the circle is going to be a solid instead of a dotted line because it's less than or equal to. So we need to connect those points with the circle, solid line circle. Okay, now we need to shade. To determine where to shade on this, we use a test point, 0, 0. 0 plus 0 is less than 25. So we're going to be shading inside the circle because that's where the test point is. Now, the other inequality, 4x minus 3y equals 0, or is greater than 0. First of all, what kind of graph is it? Well, none of the variables are squared, so it's linear. Typically, what I suggest is you find the x and y intercept. There's a slight problem with this one. If you do that, if you want to find the y-intercept, remember you let x equal 0, divide both sides by 3, and you get 0. So the y-intercept is 0. If you want to find the x-intercept, you let y equal 0, divide both sides by 4. So the x-intercept is 0. It's the same point. So all we get from that is 1 point, the origin. We need 2 points for a line. So with this one, I'd recommend we put it into slope-intercept form, y equals mx plus b. So I'm going to subtract the 4x over. So we have negative 3y is greater than negative 4x. Divide by negative 3, and remember when you divide, you flip the direction of the inequality. So that's y is less than 4/3 x. So if we have y equals mx plus b, the plus b is gone, which means b is 0. We already knew that. The y-intercept is 0. Here we have a slope of 4/3, up 4 and over 3, which would get us our next point. So from the origin, we go up 4 over 3. And this one is going to be a dotted line because it is just less than, not less than or equal to. So we have a dotted line. Now we need to determine where to shade on this dotted line. Because it goes through 0, 0, we can't use 0, 0 as the test point. So I'm going to use 1, 0. I'm going to use 1, 0 as my test point. If I plug in 1, 0 and it satisfies the inequality, then I'm going to shade towards that test point. If I plug in 1, 0 and it doesn't satisfy this inequality, I'm going to shade away from the test point. So plugging in a 1 for x and a 0 for y. This is 4 times 1 minus 3 times 0. That's 4 minus 0. 4 minus 0 is 4. 4 is greater than 0, so the test point I chose worked. It satisfied the inequality, which means it should be in the solution set for this line. So I'm going to shade on that side of the line. So then the area that contains both of the shaded regions is inside the circle on the underneath part of this line. So the solution set is this part of the circle right here. Now the vertices, the places on this solution set where the two graphs intersect, we have one right here and one right here. Now you can estimate pretty closely just based on the graph, but you have to show the exact value of these vertices using algebra. And this is the part that's from section 5.4, solving a system of nonlinear equations. So now we take this system of inequalities. To find the vertices, we change them into equations. Now, these are not like terms, so we cannot use the elimination method. We need to use substitution method. So you're going to want to get one of these variables by itself. We did that already here, so if we turn this into an equation, y equals 4/3 x, then that 4/3 x can replace y in the top equation. So that top equation becomes x squared plus 4/3 x to the second power, and that equals 25. Now 4/3 x squared means 4/3 x multiplied with 4/3 x, so that's 16/9 x squared. So we have two terms that we can combine because these are like terms. So we need to add fractions essentially. X squared plus 16/9, we have to have common denominator. So you just multiply that by 9/9. So you get 25/9 x squared equals 25. Now one way to cancel a fraction to get x squared by itself is to multiply it by the reciprocal. So if we multiply both sides by 9/25, then 25's cancel, and then the fractions cancel. So you have x squared equals 9. If you square root both sides, you get x equals positive and negative 3. So when x equals 3, we had this equation y is equal to 4/3 x. So if you plug in the 3 right here, 4/3 times 3, the 3's would cancel, so y equals 4. So we have a point 3 comma 4. When x equals negative 3, we can still use that same equation, y equals 4/3 x. If we plug the negative 3 in there, the 3's cancel, but the negative sign doesn't, so it's negative 1 times 4, so we get y equals negative 4, so the point is negative 3 comma negative 4. So those are the two. We have 3 comma 4, and here we have negative 3 comma negative 4. Question 6 is from, well, part A is from 5.1, part B is from 5.2. So part A, it says using either elimination or substitution. It doesn't say we have to use matrices, so we can use any of the methods that we talked about in chapter 5, elimination or substitution. So I'm going to use the elimination method. I'm going to multiply this top equation by negative 5. Bottom equation stays the same. We add these equations together. Now we get divide by negative 13, and we get y equals positive 3. Now if I take the original top equation from this one, x plus 3y equals 7, and plug y equals 3 right there, that's x plus 9 equals 7, so x equals -2. So for part A, x is -2, y is 3. For part B, I'm going to start with the top two equations, and I'm going to eliminate the y variable. And then I'm going to take, so this was equation 1, this was equation 2. For the second part of it, I'm going to take equation 1 and equation 3. So the top equation and the bottom equation, and add those together and eliminate the same variable. Remember, when you're doing 3 equations, for step 1 you eliminate a variable. For the second part, you eliminate the same variable from 2 other equations. So now we have 4x minus 2z equals 4. So now if we combine these two, the result from step 1 and the result from step 2, we have 2x plus 2z equals 14. Here we're going to have 4x minus 2z equals 4. So we can combine these two to eliminate z, divide by 6, and we get x equals 3. So now we can take x equals 3 and go back to one of these smaller equations that only had 2 variables. We can solve for z. I'm going to take this one here. So 4x minus 2z equals 4. If you plug in an x equals 3 right there, that becomes 12 minus 2z equals 4 minus 12, so we have negative 2z equals negative 8. Divide by negative 2, I'm going to get z equals 4. And finally, if we take one of the original equations, like the top original equation from part B, we have x minus 2y plus 3z equals 1. X equals 3, so that becomes 3 minus 2y, and then if z is 4, 3 times 4 is 12, so that's plus 12 equals 1. Combine the 3 and the 12 to make 15, subtract 15, divide by negative 2, and y equals 7. So the result would be x equals 3, y equals 7, and z equals 4. 20 plus 18. Number 12 is from section 6.3. On part A, the first step is to create the matrix equation. Second step would be to find the inverse of this matrix, because we need to multiply by that inverse here and here. So we need to find the inverse of that matrix. So assuming we're going to call this one matrix A, the inverse of that would be inverse of A. Remember the formula is AD minus BC. D and A change spots. B gets multiplied by -1, and C is multiplied by -1. So this is 1 divided by A times D is -20, minus B times C, it's -18, -4 and 5 change spots. -3 gets multiplied by -1, so that's 3. 6 gets multiplied by -1, so that's -6. -20 minus -18 minus -18 is plus 18, so -20 plus 18 is -2, so this is -1/2. So what happens next, after you have the inverse, is it multiplies on the left side of this. That's just going to reduce this matrix to the identity matrix, which essentially is the number 1. You don't need to show that multiplication. What you need to show is that you've multiplied the inverse to this matrix. So the next part of this would be our inverse matrix. Multiplied by this matrix here. So this entry is going to be a combination of this row and this column. -4 times 5, that's -20. 8 times 3 is 24. -20 plus 24 is 4. This entry is a combination of this row combined with that column. So -6 times -4, that's 24. -4 times 8 is -32. So 24 minus 32. That's -8. Then we take the -1/2 and multiply it into this matrix. So it's -1/2 times 4, -8. That gets us -2 and +4. So x is -2 and y is +4. Now for part B, we start by creating the matrix equation. So the first matrix is all of the coefficients from the original system equation. So we're going to have 1, -2, and +2. And then 2, -3, 1. And for the bottom equation, we have 0, 1, -1. Then we have the matrix containing the 3 variables. And then the matrix at the end is -12, -10, and 6. Now, if we were to proceed like we did in part A, we would have to find the inverse of this matrix. Luckily for us, finding the inverse of a 3 by 3 matrix is quite difficult. It's been given to us right here. We use that as the inverse. So the inverse is given to us. And then really all we need to show is that we multiply it with this matrix here. Okay, so this entry is going to come from a combination of that row and this column. So it's negative 12 times 1, that's negative 12. 0 times 10 is 0. 2 times 6 is positive 12. So we had a negative 12 here, we had a 0 here, and a positive 12. Add those together, and we get 0. The next entry is a combination of this row with that column. So negative 12 times 1 is negative 12. Negative 1 half times negative 10 is 5. And then 6 times 3 halves is 9. So we have negative 12 plus 5, it's negative 7. Negative 7 plus 9 is positive 2. Finally here, this entry is a combination of that row and that column. 1 times negative 12 is negative 12. Negative 1 half times negative 10 is 5. And then half of 6 is 3. So we have negative 12 plus 5, that's negative 7. Plus half of 6 is 3. So negative 7 plus 3 is negative 4. So the solution is 0, comma 2, comma negative 4. And it would have been a good idea for part A. It's a better idea even for part B to check your solution. So if we take 0, 2, and negative 4, come back to the original. If x is 0, y is 2, and z is negative 4, we're going to have 0. 2 times 2 is 4, so 0 minus 4, that's negative 4. And then if z is negative 4, that makes negative 8. Negative 4 plus negative 8 is negative 12. Here we have 0 minus 6 minus 4, that's negative 10. Here we have 2 minus negative 4, which is 6. So the solutions check out in all three equations. Okay, for part A, the determinant of a 2 by 2 matrix is just A times D minus B times C. So it's 6 minus 8, which is negative 2. For part B, I'm going to use the method that was presented in class. I'm going to copy the two columns here on the right side of the matrix. And then we have to multiply a couple numbers together and then add, subtract. There's a lot to keep track of here. So you always start in the top left corner, going down to the bottom right. This process always begins there. So the product of those three numbers is 3. We're always going to add here to begin with. So these first multiplications that we do, these always add. The next multiplication is 0 times 2 times 4, that's 0. And again, we always add to begin with. For the first 3 rounds, we add. The next round is 4 times 2 times 6, that's 8 times 6, that's 48. Now, the next 3 rounds, we're subtracting, and now we're going in a different direction. We start at the bottom left, right here. So 4 times negative 3, that's negative 12. Negative 12 times negative 4 is negative 48. So, or positive 48 rather. So we subtract positive 48. The next one is 6 times 2 times 1, so that's a positive 12, so we subtract 12. And then negative 1 times negative 2 times 0 is 0. 48 minus 48 is 0. So it's essentially 3 minus 12, which is negative 9. And I apologize for not stating this at the beginning. Determinants of matrices is from section 6.4. Okay, question 14. These are from 8.1, 8.2, and 8.3. So what we have in part A is obviously we're adding numbers together, and there's no end. This is an infinite sum, that you can only find the infinite sum if it's a geometric sequence. So first we have to determine what kind of sequence this is. The terms of the sequence are 7, 7/2, 7/4, 7/8. So to go from 7 to 7/2, you multiply by 1/2, and then to go to 7/4, you multiply by another 1/2. So we're multiplying by 1/2 to go from this term to that term to that term. So since we're multiplying by the same number, 1/2, that makes it geometric. The other thing to remember is in order to use the infinite sum formula, the common ratio has to be less than 1. And here the common ratio is 1/2. So this is geometric. Geometric because we have a common ratio of 1/2, and that is definitely less than 1. So the sum, the infinite sum, is the first term divided by 1 minus r. The first term is 7. So it's 7 divided by 1/2, which is 14. For part B, this is another sum. This is sigma. So we're finding a sum. We're doing the first term all the way to the 27th term. So we're adding 27 terms. So this is not an infinite sum. This is a partial sum. We look at the nth term formula. 5n minus 3 is linear. That means this is an arithmetic sequence. So we need the partial sum formula of an arithmetic sequence. N stands for the number of terms. We're adding 27 terms. A sub 1 is the first term of the sequence. We can find the first term using the nth term formula by plugging n equals 1. 5 times 1 is 5. 5 minus 3 is 2. So the first term is 2. Now a sub n is really a sub 27 because it's the 27th term. So the 27th term we find by plugging in 27. 5 times 27 is 135, and 135 minus 3 is 132. So we replace now n is 27, so this is 27 divided by 2. The first term a sub 1 is 2, and then the last term there, the 27th term rather, is 132. And then multiply those two together to get the sum of the first 27 terms. And that's 1,809. Now remember, oh, finally we have section 8.6, the last problem, Pascal's triangle or the binomial theorem. What we learned was to use Pascal's triangle to answer the following question. So for part A, we're just expanding 3x minus 2 to the 4th power. So we need the first 5 rows of Pascal's triangle. For this one, that's going to tell us the coefficients. So for the first term, we're going to have a coefficient of 1. And then we have this term to the 4th power. And remember that everything here needs to be in a parenthesis. And technically, we also have this term to the 0 power, but that's just 1. And next term is going to have 4 as a coefficient. Going to have 3x to the 3rd power now. And then the next term, negative 2, is to the 1st power. Next, we're going to have a coefficient of 6. And then 3x is to the 2nd power. Negative 2 is also to the 2nd power. Here we're going to have a coefficient of 4. 3x is to the 1st power. Negative 2 is to the 3rd power. And finally, we have a coefficient of 1. 3x is to the 0 power, which we don't need, but negative 2 is to the 4th power. So 1 times 3x raised to the 4th power is 81 x to the 4th. This is going to become 4 times 27 x to the 3rd times negative 2. This becomes 6 multiplied by 9x squared times positive 4. This is 4 times 3x times negative 8. And this is negative 2 to the 4th power is 16. So now the only thing that's left is multiplying any coefficients to make one coefficient. So the first term is just 81 x to the 4th. The next term is 4 times 27 times negative 2. So we need to figure out what 4 times 27 times negative 2. That's negative 216. So I'm actually going to change the plus to a minus 216 x to the 3rd. Now this one is 6 times 9 times 4. That's 54 times 4, which is also 216. Is positive 216, so it can be plus 216 x squared. This term is 4 times 3 times negative 8. That's 12 times negative 8. That's negative 96. So since it's negative, it's going to be minus 96x plus 16. Now part B, they're not asking for the entire expansion. They're asking for one particular term. It would be like picking out, just one term from the entire expansion, and it's a particular term that's going to contain y with an exponent of 4. Since this is to the 6th power, we need actually a couple more rows here from Pascal's triangle. We need 7 rows because this is to the 6th power. So this is the 7th row. And we need the term that contains y to the 4th. So if you start at the very beginning, this term contains an x to the 6th and a y to the 0. The next term is going to contain an x to the 5th and a y to the 1. This is going to contain x to the 4th and a y squared. This is going to contain x to the 3rd, y to the 3rd. This one's going to have x squared and y to the 4th. So we need this as the coefficient. This is the coefficient of the term that has a y to the 4th. It also has an x squared. So we're going to take that 15 as the coefficient. The first part of this, 2x, that's going to be raised to the 2nd power. The next part of it, 3y, is going to be raised to the 4th power. So this is 15 times 4x squared times 81 y to the 4th. So we just need to figure out 15 times 4 times 81. And that's 4,860. And then we're going to have an x squared and a y to the 4th.